Okay, let's go ahead and get started. This should, this note sheet should make it go faster. And yes, you may use this on your open note test, and I will.
Hey guys,
Okay, so what we're going to look at is predicting products, and this is what you're going to have to do in the lab. And we'll practice today, we'll practice tomorrow. So basically, I'm going to give you guys some rules so you're able to figure out what products are made from whatever reactant, okay? So we're going to start with combustion reactions. And so at this point, when you're predicting products, okay, you're going to look at the reactants and you're going to look and you're going to say, okay, do I have two ionic compounds? Do I have oxygen combining with a single element? Do I have one single reactant? So we're going to look at the reactants and try and figure out what's made. And that's what you're going to do in the lab, okay? I'm going to give you your reactants, and then you're going to use this to help you decide what is made, as well as all of the observations from the lab to help you figure out what's actually made as products, okay? It's not too tough, okay? It's just probably something you guys haven't done before. So we're going to start with combustion reaction, okay? So if we have a single element combining with oxygen, so like we did in the notes before, we represented a single element with A, and if it is combining with oxygen, you will always get a binary compound, okay? So a binary compound. Always get a binary compound. So A plus O, okay, is going to give you AO. That's your binary compound. You're just going to put the two elements together. Whatever element you have here, combine it with oxygen. You'll have to check your oxidation numbers to make sure your formula is correct. But it's just that simple, okay? You get a binary compound, okay? So an example might be, let's see, barium, okay, plus oxygen will give you barium oxide. Now you always have to check your oxidation numbers and make sure that your formula is correct, okay? And it is. And then you might have to go back and balance it. So to balance this, where would I put coefficients? So do I need a coefficient here? In front of the barium. Very good. So if it is a combustion reaction, you take the two elements, you put them together, okay, to make your binary compound. Check your oxidation numbers, and then balance if necessary. Okay. So the second type, okay, of combustion reaction is a hydrocarbon plus oxygen. Okay. So your hydrocarbon plus oxygen, so like some compounds CXHY, we don't know what the subscripts are yet. So if we have a hydrocarbon and it is combining with oxygen, the products will always be carbon dioxide and water. If you have a hydrocarbon, and sometimes this hydrocarbon actually has oxygen in it, but if you have a hydrocarbon combining with oxygen, those are your products regardless, okay? No matter what. So if I said methane gas, okay, burns in the presence of oxygen, so if I gave you those products and you were like, oh, that's a hydrocarbon and that's oxygen, oh, it's combustion, you automatically know that water and carbon dioxide is made. Always. There's no doubt about it. Okay? Those are our combustion reactions. So you'll be given the reactants, and then you have to come up with the product. These ones aren't too bad. Those ones are pretty easy. Okay, so our synthesis reactions, let me move over here. Okay, so again, not too tough. If we are doing synthesis reactions, and when you do the lab, it's broken up. I say, okay, these are synthesis reactions. You're doing two synthesis reactions. You're going to actually do the reaction, okay, and this is going to help you come up with the product, okay, as well as all your observations, like I said. Okay, so synthesis, if you have a metal combined with a non-metal, you just put them together and make it a binary compound, okay? So a metal and a non-metal, you make a binary compound. And a lot of times they call that binary compound a salt, okay? It's an ionic compound, okay? So sodium plus chlorine will give us sodium chloride. You just put the two together. Always have to check your oxidation numbers and then balance if necessary. Okay, that's the first one. Super easy. If we have the second one, if we have a metal oxide combined with water, okay, so metal oxide, so that metal could be anything. That could be sodium, it could be magnesium, it could be iron, it could be anything. So if you have a metal oxide and it's combining with water, you're going to make a metal hydroxide. So we're going to put whatever metal is in our reactant, and we are going to pair it up with the polyatomic ion hydroxide. So we'll take the metal from the reactant and we pair it up with hydroxide. We check our oxidation numbers. Who needs the subscript, barium or hydroxide? Hydroxide. Okay. So this could be any metal. So if it was magnesium oxide and water, it would give me magnesium hydroxide. If this was sodium hydroxide and water, I would get, or sodium oxide and water, I would get sodium hydroxide. It always turns out to be that. Okay. Our next one is a metal chloride and oxygen. So if we have a metal chloride combined with oxygen, we always get a metal chlorate. Always. So again, this metal could be anything. Could be calcium, could be barium, could be magnesium, could be iron, it doesn't matter. If I have a metal chloride combined with oxygen, I'm going to get a metal chlorate. So I take the metal from the reactant, which is calcium, and I pair it up with chlorate. Does anybody remember the formula for chlorate? The polyatomic ion? Nobody wants to take a stab at it? ClO3. Very good. So I take the metal from the reactant, I pair it up with chlorate, check my oxidation numbers. Calcium is +2, chlorate is -1. So who needs the subscript? Chlorate. Like that. Again, that metal could be anything. So it could be magnesium chloride. It could be barium chloride. It could be strontium chloride. Doesn't matter what it is. If it's combining with oxygen, it'll make a metal chlorate. Second to last one. This is a metal oxide. So any metal with oxygen combined to it and carbon dioxide. So again, this could be magnesium oxide, zinc oxide, copper oxide. If it's a metal oxide and it's combining with carbon dioxide, we will always get a metal carbonate. Always get a metal carbonate. So I'm going to take the metal, okay, from my reactants, and I'm going to pair it up with carbonate. Okay, so Fe, carbonate's a polyatomic ion, so CO3. Now, we got to check our oxidation numbers. However, you guys remember iron could have more than one oxidation number? So this is what we have to do. We have to look to what he's bonded with and figure out what oxidation number he is on this side. So oxygen is -2, right? And we only have one iron atom. So what's iron's oxidation number in this compound? 2 plus. So if he's 2 plus on this side, he's 2 plus on this side. So if iron's +2 and carbonate is -2, do I need subscripts? No. Now it needs to be balanced, but we won't do that right now. We don't have enough time. Our very last one is a metal and oxygen to make a metal oxide. I didn't do an example because this is basically the same thing, but we can write one. Metal and oxygen. So let's say, let's go strontium and oxygen. We're going to make a metal oxide. So we're just going to stick the two of them together. SRO. Strontium is +2. Oxygen is -2. So I don't need any subscripts. This is your guide. Okay. And yes, you may use this on the test. This is a lot of information. Okay. And you're going to have an assignment that you can practice this tomorrow. Okay, so decomposition reaction. Okay, so in a decomposition reaction, if you have a metal and a non-metal, if you have a binary compound, the only thing that can happen is the two can break apart. That's it. Okay, there's no other option. Okay, so I'm going to put barium plus chlorine. How come I'm putting a little 2 next to chlorine? He's a diatomic molecule. Now, if you remember, these are literally the exact opposite of synthesis reactions. Okay? Now, again, this isn't balanced, or it actually is balanced. Okay, so if we are starting with a metal carbonate, it's going to make a metal oxide and carbon dioxide. So a metal oxide is the metal and oxygen combined. Okay, so that's my first product. Okay, so the metal in my reactant is calcium. It's a metal oxide, so I'm going to pair them up with oxygen. And calcium is +2, oxygen is -2, so I don't need subscripts. And is plus carbon dioxide. So if you are starting with a metal carbonate, it will always break into a metal oxide and carbon dioxide. Always does. Again, that metal could be anything. Barium, magnesium, iron, okay? It's still going to break into a metal oxide and carbon dioxide. Metal hydroxides. So metal hydroxide is going to make a metal oxide and water. So I'm going to take the metal from my reactant and I'm going to pair it up with oxygen, a metal oxide. I'm going to check my oxidation numbers. Sodium is +1, oxygen is -2. So who needs my subscript? Sodium needs a 2. So that's my metal oxide and water. So every metal hydroxide breaks into a metal oxide and water all the time. Metal chlorates. So a metal chlorate, okay, is going to break into a metal chloride and oxygen gas. So I take the metal from my reactant and I'm going to pair it up with chlorine. So a metal chloride is KCl. I'm going to check my oxidation numbers and I don't need any subscripts. And is plus. What's special about oxygen by himself? He needs a diatomic, he needs a subscript too. Now I'd have to go back and balance it, but I'm not going to. So any metal chlorate will break into a metal chloride and oxygen gas. The very last one, this one's basically the same as a binary compound or a salt. But if you have a metal oxide, the only thing that it can break into is its two original elements. Okay, so we're just going to break them apart. We're going to make this guy iron, and we're going to make this guy oxygen. that's it. I mean, there's nothing you can do. Okay. Let's move. Are we okay? Not too bad? Okay. So let's look at these instructions, and then we'll move to some practice problems. So activity, like it says, is the ability of an element to react. So like if something is very active, it's very reactive. Okay, like it reacts very readily. If something is not very active, if it has low activity, it's not very reactive. So we have something called the activity series, and you guys have it right in front of you. This guy is your activity series. We only use this on single replacement reactions. So if you want to write single replacement so you remember, we only use the activity series on the single replacement reaction. This activity series gives us a list of the most reactive metals, or I should say the most reactive cations, all the way through here because hydrogen can be a cation. So the most reactive cations from top to bottom, and then our most reactive to our least reactive halogens. Okay, so of all of our metals on the periodic table, okay, lithium is the most reactive. It has the highest activity, and then activity decreases as you go down. Okay, so this guy is going to be more reactive than magnesium. Rubidium is going to be more reactive than cobalt. So reactivity is going to decrease as you go down the list. Same thing with our halogens. Fluorine, and you guys knew this already, it's the most electronegative element, so it is the most reactive, and then it goes all the way down to the least reactive halogen. Okay, so we're going to use the activity series to help us predict our products. So back to this guy right here. It says the most active elements or reactive elements can replace any element below it. Okay, so like I was saying, elements at the top can replace anything below it. However, elements from the bottom cannot replace anything above them. Okay, so anything at the top can replace anything below it. Okay, anything like, you know, rubidium is below lithium, so rubidium would not replace lithium. Lithium could replace rubidium, but not in the opposite direction. Sodium is less reactive than lithium, so sodium could not take the place of lithium. Does that make sense? Okay. So the most active elements can replace any element below it. An element cannot replace an element above. I just told you that. So sometimes no reaction is possible. So sometimes when we're doing this on paper, you might actually, in the product, say no reaction, like this doesn't actually happen. Metals replace cations, non-metals replace anions. We talked about that yesterday. The single element must be above the element it is trying to replace. So let's just do some of these. I think it's easier just to do them. Okay, here's two examples. So the first thing I have to identify is my single element is a metal. Okay, so I'm going to look to my compound, and I'm just a visual person. I'm going to underline my cation, which is copper. So what I have to do is I have to see, okay, is iron above copper in my activity series. So in order for iron to take the place of copper, he has to be above copper in the activity series. So I'm going to come to my activity series, and I'm going to see, is iron above copper? So let's see, where's iron? Yes, I take your word for it. Iron is above copper. Perfect. Okay, so that means iron can replace copper. So that means my reaction is going to happen. So what I'm going to do is I'm just going to flip them spots. I'm going to flip spots. I'm going to pair iron up with sulfate. And who's going to be left all by himself? Copper is going to be left all by himself. Okay, so we're kind of stuck here for a second because I still need to balance this guy out. Okay, however, as you guys remember, we just talked about iron has more than one oxidation number. Okay, since iron is all by himself, we don't know what oxidation state he's going to take when he's with sulfate because he wasn't in a compound before, right? So grab your periodic table. Find iron. And when you're stuck in this position, can you see how 3 is the very first oxidation number and it's bolded? That means that's the most common oxidation state. So that's the oxidation state we're going to use. Okay? So I'm going to go back, and 3 was the most common, so I'm going to put plus 3 here. We know sulfate is minus 2. So I'm going to make my formula correct. I'm going to put a 2 here, and I'm going to put a subscript 3 here. And then I would have to go back and I would have to balance it. Does that make sense? So what, we would have to put a 3 right here, right? Give me 3 sulfate, 3 copper, and I have to put a 2 right here. So let's do the next one. I identify my single element. Is he a metal or is he a non-metal? Non-metal. So he's going to look to replace the anion. Okay? So I have to look at my activity series. Is bromine above chlorine in my activity series? So is bromine above chlorine? No. If that happens, all we say is we say no reaction. Can't happen. Let's do one more of those. Let's do one more. Let's do cadmium bromide plus iodine. Okay. So my single element, is he a metal or a non-metal? Non-metal. So he's going to look to replace the anion in my compound. So we have to check to see, is iodine above bromine? We always look, is the single element above bromine? It is not. So I'm going to simply say no reaction. I don't really want to use that one. That'll work. Let's do one more. Let's do HCl plus zinc. My single element, is he a metal or is he a non-metal? What is zinc, a metal or a non-metal? He's a metal. So he's going to look to replace the cation in my compound. So we have to see, is zinc above hydrogen in my activity series? Is he? I believe you. So that means the switch can happen. So zinc is going to take the place of hydrogen. So I'm going to have zinc chloride. Zinc is plus 2, chlorine is minus 1. So I need a subscript here. And which element is all by himself? Hydrogen. And I would need a subscript 2 right next to it. Those are single replacement reactions. And let's, gosh, we've got good timing. Okay, so double replacement reactions, okay? So number 1, it says, check solubility chart to make sure both reactants are aqueous and write the symbol. Okay, we'll practice this. Let's just look at these. If a reactant is something other than aqueous, then the reaction will not happen. No reaction. Switch cations in the reactants to make new products. Pair up new cations and anions. check oxidation numbers, add subscripts, balance if necessary. Check solubility chart to make sure at least one product is soluble, which is a precipitate, gas, or liquid. Both products cannot be aqueous. That would be no reaction. So this is that reaction I was telling you guys about, that it makes a difference to have your state of matter symbols. Like, they're required for these reactions, because if we don't check the state of matter, we don't know if the reaction actually occurs. Like, this time it's necessary. Okay, so a few key things. First of all, both reactants have to be aqueous. If both reactants are not aqueous, the reaction does not happen. Okay, they both have to be aqueous. In your products, one product has to either be solid, gas, or liquid. Okay, if both are aqueous in my products, then no reaction happens. So we always start with the reactants, and we are always going to check to see if they're aqueous. That's our first step. So let me show you how to use our solubility chart right here. And I'm going to unzoom it a little bit, since you guys have it in front of you. Okay, so next to soluble, up here, write AQ. So if something is soluble, it is going to be aqueous. Insoluble, put a little S. And on the top of this, write double replacement reaction. So you're only going to use this for double replacement reactions. This is how we read this. So phosphates, carbonates, bicarbonates of ammonium, meaning phosphates, carbonates, bicarbonates that are bonded to ammonium, are aqueous. Phosphates, carbonates, bicarbonates that are bonded to alkali metals are soluble, unless they're bonded to lithium. Okay? Except for, this means if you have phosphates, carbonates, bicarbonates, okay, with all other cations, they're going to be a solid, or they're going to precipitate out. Okay? So phosphates, carbonates, bicarbonates of ammonium are soluble, and if they're bonded to alkali metals, they are soluble, except for lithium, okay, and most other cations are going to be solid. Now, once we start practicing this, it gets super easy. Almost all salts are just ionic compounds, so don't let that freak you out. Almost all salts of alkali group and ammonium and hydrogen are soluble. So salts of alkali group and ammonium and hydrogen are soluble. They're always aqueous. All salts of chlorine, bromine, and iodine, okay, so it means if these guys are bonded to metals, they're going to be aqueous, okay, unless these guys are bonded to these, okay. These guys bonded to these will be solid. Salts of fluorine, that just means fluorine bonded to a metal, okay, are all going to be aqueous unless fluorine is bonded to these, then it's soluble. Nitrates, so this means if a metal is bonded to a nitrate, if a metal is bonded to a chlorate, okay, if a metal is bonded to a perchlorate, they're always aqueous. There's no exception. Acetates, all acetates are going to be aqueous unless it's bonded to silver, then it's going to be solid. All sulfates are going to be aqueous unless it's bonded to one of these three, then it's going to be solid. Sulfides bonded to ammonium will be aqueous. Sulfides bonded to group 1 or group 2 elements will be aqueous. Everything else sulfur is bonded to is going to be solid. And like I said, once we get going, it's going to be easier. Hydroxides bonded to ammonium, okay, are aqueous. Hydroxides bonded to alkali metals are aqueous. Hydroxides bonded to barium and strontium are aqueous. Hydroxides bonded to all other cations are insoluble. That's how you read this. And I know it's a little overwhelming, so just hold tight, okay? Let's do an example or two. I'm just going to get a blank sheet of paper. You can, if you need to do, if I don't give you enough practice room, then, okay. Let's do magnesium sulfate plus calcium acetate, C2H3O2 yield. Let's do this one first. So that's magnesium sulfate plus calcium acetate. So the first thing we are going to do, now we're trying to predict the product. We are going to come to our solubility chart. And I'm always going to look up my anion. So I'm going to look up my sulfate. Okay? So sulfates are aqueous unless it's bonded to strontium, barium, and lead. So it's bonded to magnesium, so it's not one of these three, so it's going to be aqueous. So what I'm going to do is I'm going to put AQ right next to this guy. Okay. Now I'm going to move over here. I always start with my anion, which is acetate. So I'm going to come over here. Acetates are aqueous. Okay, so acetates are aqueous unless they're bonded to silver. Well, this guy's bonded to calcium, so he's aqueous. I'm going to put AQ right here. So that tells me, hey, the reaction can happen. Okay? If this was a solid, or if this was a liquid, or if this was a gas, the reaction can happen. So now what I do is I'm going to identify my two cations. And I'm going to switch places. I'm going to make them switch places in my product. Let's see if I can make that a little bit bigger. Okay, so I'm going to pair them up. I'm going to pair up magnesium with acetate. So I'm going to put Mg C2H3O2. Put those two together. I'm going to check my oxidation numbers. Magnesium is +2, acetate is -1. So my acetate needs the subscript plus. So now I'm going to pair up calcium with sulfate. So it's going to be CaSO4. Check my oxidation numbers. And I'm good. Now I got to go back to my solubility chart. Okay. Now I have to see which one is the precipitate, which one forms that cloud. Okay. And if it's a solid, okay, or if it's insoluble, that's my precipitate. So I'm going to go back. Acetates, I'm going to go back over here. And acetates are all aqueous. Oh gosh, I got too zoom. So acetates are aqueous unless they're bonded to silver. Okay, so it's bonded to magnesium. So I'm going to put AQ right here. I'm going to go back to my solubility chart and I'm going to look for sulfates. Okay, sulfates are aqueous unless it's bonded to strontium, barium, or lead. So is this bonded to strontium, barium, or lead? Nope. So this guy is aqueous. This means that this cannot happen. No reaction. I have to have a solid, a liquid, or a gas in my product for the reaction to occur. You stop there. When you find out no reaction, you don't go any further. You don't balance it. You don't do anything with it. You just stop. Okay? We're going to do one more. I'm going to get a different sheet of paper. Can you guys see that? I don't have enough room to do all my work. NH4Cl. Oh my goodness. NH4Cl plus barium hydroxide. Yield. Okay. First thing we got to do is we have to see if the reaction even happens. So we're going to look up our solubility chart. And I always look for my anion. So my anion in the first compound is chlorine. I'm going to go to my solubility chart and I'm going to find chlorine. Okay? Chlorine is aqueous unless it is bonded to silver, mercury, lead, or thallium. So, is it bonded to? It's not bonded to any of those. So he's aqueous. I'm going to look for hydroxide. Come to my solubility chart. And I'm going to find hydroxides, which are down here on the bottom. Hydroxides of ammonium are aqueous. It's not bonded to ammonium. So hydroxides bonded to alkali metals, barium and strontium are soluble or aqueous. So it's bonded to barium, so he's AQ. You guys with me so far? Awesome. So this means so far, it means the reaction can happen. So far. So I'm going to identify my two cations. And I am going to switch these guys' places. So I'm going to take my barium, and I'm going to pair it up with chlorine. Barium is +2, chlorine is -1, so I'm going to get 2 here. And I am going to pair up my ammonium with hydroxide. So NH4OH. This guy is +1, that guy is -1. So now I got to go back to my solubility chart and see if I get both aqueous or if I end up with a solid or a gas or something else. Okay, so we go back to chlorines. So chlorines are aqueous unless it is bonded to silver, mercury, lead, or thallium. And it's not bonded to any of those, so this guy is aqueous. Ammonium hydroxide. So again, I'm going to look up my hydroxides. Okay, so two bad examples. Hydroxides of ammonium are aqueous. Aqueous, can that happen? Not happen. So I'm going to say no reaction. And I'm done. If, like I said, I picked two bad examples. If one of these is solid, you're good to go. Okay? The next step would be to balance it out. Okay? So if your two products, if one is aqueous and one is solid, that means reaction happens. okay? And you would have to proceed to just balance it, okay? You have 3 of these in your lab, okay? And tomorrow we're just gonna practice a bunch, okay? You're done. You maxed out your brains for the day, and you were patient, and you did fantastic. So, very good.